The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today we are introducing an exciting new pledge in 6034. Anyone who has already looked at any of the neural net problems will have easily been able to see that even though Patrick only has them back up to 2006 now, there still are, well, out of 4 tests, perhaps 2 or 3 different ways that the neural nets were drawn. Our exciting new pledge is we're going to draw them in a particular way this year. And I will show you which way, assuming that this works. Yes. We are going to draw them like the way on the right. The one on the left is the same as the one on the right. At first, not having had me explain the difference between the two of them, you might think you want the one on the left, but you really want the one on the right. And I'll explain why. The 2007 quiz was drawn roughly similarly to this. Also, if you somehow wind up in tutorial or somewhere else doing one of the older quizzes, a lot of them were drawn exactly like this. In this representation, one thing I really don't like is that the inputs are called X's and the outputs are called Y's, but like there's 2 X's, so the inputs are not X and Y, and then they often correspond to axes of a graph, and then people get confused. Additional issues that many people have are the fact that the summation and the multiplication with the weight is implied. The weights are written on the edges where outputs and inputs go. And the summation of the 2 inputs into the node is also implied. But take a look here. This is the same net. These W's here would be the W's that are these W's here would be the W's that are written into onto these lines are here. Actually, the better way to draw it would be like, better way to draw it would be like so, since each of these can have their own W, which is different. So each of the W's that are down here are being explicitly sent through a multiplier, whereas here you just had to remember to multiply the weight by the input that was coming by. Here you see an input comes to a multiplier, you multiply by the weight. Then once you've multiplied all the inputs by the weight, you send them through a sum. That's the sigma is just a sum. You sum them, add them all up together, send the result of that into the sigmoid function, our old buddy, 1 over 1 plus e to the negative whatever our input was, with a weight for an offset. And then we send the result of that into more multipliers with more weights, more sums, more sigmoids. So this is how it's going to look like on the quiz. And this is a conversion guide from version 0.9 beta into version 1.0. So if you see something that looks like this on one of the old quizzes that you're doing, see if you can convert it and then solve the problem. Chances are, if you can convert it, you're probably going to do fine. So we'll start off not only with this conversion guide, but also yeah, I'll leave that up here. Also, I'm going to work out the formulae for you guys one more time. These are all the formulae that you're going to need on the quiz. And then we're going to decide what will change in the formulae if, and this is a very likely if, there seems to be a good amount of times that this happens, if the sigmoid function in those neurons up there was ever changed into some other kind of function. Hint, it's changed into a plus already in the problem we're about to do. People change it all the time into some bizarro function. I've seen arctangent, I think. So here we go. let's look at the formula. First of all, sigmoid. Well, our old buddy sigmoid, I just said it a moment ago. Sigmoid is 1 over 1 plus e to the minus x. Also, fun fact about sigmoid, the derivative of sigmoid is itself, the derivative of sigmoid is, let's say that the sigmoid, we'll just turn sigmoid into like the letter, say y. Y is the result, right? So if you say y equals 1 over 1 plus e to the negative x, then the derivative of sigmoid is y times 1 minus y. You can also write out the whole nasty thing. It's 1 over 1 plus e to the negative x times 1 minus 1 over 1 plus e to the negative x. It's a nice property of sigmoid. It's going to be important for us in the very near future, and that future begins now. So now, the performance function. This is the function we use to tell our neural nets when they inevitably act up and give us really crappy results. At first, we tell them just how wrong they are with our performance function. The performance function can be any sane function that gives you a better score, where better can be decided as lower or higher if you feel like it, but gives you a better score if your answers are closer to the answer you're looking for. However, in this case, we have, for a very sneaky reason, chosen the performance function to be 1/2 d, which is the desired output, minus o, the actual output, squared. So we want a small, well, it's negative, so we want a small negative or a 0. That would mean we performed well. So why this? Well, the main reason is ddx of performance is, the 2 comes down, the O is the variable that we're actually D'ing, so maybe I should say DDO. That negative comes out, we get a simple D minus O. And yeah, we're using derivatives here. So those are fine. These are 2 assumptions. They could be changed during the test. We're going to figure out what happens if we change them. If we change the performance, if we change the sigmoid, if we change the sigmoid to some other function, what's going to happen to the next 3 functions, which are basically the only things that you need to know to do backpropagation. So let's look at them. First, W prime. This is the formula for a new weight after 1 step of backpropagation, a new weight in any of these positions that you can see up here on this beautiful neural net. That W, each of the W's will have to change step by step. That's in fact how you do the hill climbing neural nets. You change the weights incrementally. You step a little bit in the direction towards giving you your desired results until eventually, you hope, you have an intelligent neural net. And maybe you have many different training samples that you run it on in a cycle, hoping that you don't overfit to your 1 sample on a computer. But on the test, we probably will not do that. So let's take a look at how you calculate the weights for the next level, given that you have the weights for the current level. So first things first, new weight, weight prime, starts with the old weight. That has to go there because otherwise we're just going to jump off somewhere at random. We want to make a little step in some direction. So we want to start where we are with the weight. And then we're going to add 3 things. So if we're talking about the weight between some I and some j, here are some examples of the names of weights. So this is W1I. That's the weight between 1 and A. Oh, so this is W1A. It's the weight between 1 and A. This is W2B, which is the weight between 2 and B. Make sense? Well, it makes sense so far, but what if it's just called WB? Then it's the weight between these W's that only have 1 letter. We'll get to later. They're the bias. They're the offset. They are always attached to a -1. So you can pretty much treat there as being like a -1 here that is then fed into a multiplier with this WB, if you like. This is implied to be that. All of the offsets are implied to be that. So, W plus some alpha. Why is it a Greek letter? Where does it come from? How do we calculate it? Well, alpha is just some value told to you on the quiz. You'll find it somewhere. There's no way you're going to have to calculate alpha. You might be asked to try to give a say in alpha, but probably not. Alpha is supposed to give the size of our little steps that we take when we're doing hill climbing. Very large alpha, take a huge step. Very small alpha, take tentative steps. So alpha is just there to change, basically to change this answer in to make the new value either very close to W or very far from W, depending on our taste. So plus alpha times I. So I is the value coming in. I is the value coming into the node. We're changing the weight here. So I is the value, for instance, I sub 1 here. I would be the value at WAC. I would be the value coming output of node A. At WBC, I would be the output of node B. I is sometimes specifically labeled as I. I is the input coming in to meet that weight at the multiplier. And then it's multiplied by delta J, where delta is the delta that belongs to these neural net nodes. What is a delta, you say? Funny you may ask. It is a strange Greek letter. It sort of comes from the fact that we're doing some partial derivatives and stuff, but the main way you're going to figure out what the deltas are these 2 formulae that I have not written in yet. So hold off on trying to figure out what the delta is until, well, right now, because I'm about to tell you what the delta is. So the delta is basically, think of the delta as using partial derivatives to figure out which way you're going to step when you're doing hill climbing. Because you know when you're doing hill climbing, you like look around, you figure out, okay, this is the direction of the highest increase, and then you step off in that direction. So the deltas are sort of telling you which way to step with the weights. And the way they do that is by taking the partial derivative of, basically you try to figure out how the weight that you're currently looking at is contributing to the performance of the net, contributing to either the good performance of the net or the bad performance of the net. So when you're dealing with the weights like WBC and WAC that pretty much directly feed into the end of the net, they feed into the last node, it then comes out, it's the output, okay, then that's pretty easy. You can tell exactly how much those weights and the values coming from them are contributing to the end. And we do that by, first, we do that by essentially, we remember what the partial derivative. So the partial derivative here is in fact, the way that the final weights are contributing to the performance is just a performance function. Partial derivative, well, I've already figured out the derivative here. It's just d minus O. This is for sort of final weights, the weights in the last level. D minus O, it's that we're not done yet because when we do derivatives, remember the chain rule. To get from the end to these weights, we pass through, well, it should be a sigmoid. Here it's not. We're going to pretend it is. Pretend it is for the moment. We pass through a sigmoid. And since we pass through the sigmoid, we better take the derivative of the sigmoid function. That is y times 1 minus y. Well, what is y? What is the output of this sigmoid? It's O. So that's also multiplied by O times 1 minus O. However, there is a, let me see. Yes. Sorry, I'm carefully studying the sheet to make sure my nomenclature is exactly right for our new nomenclature, which is so new and brave that we're doing it that we only knew for sure we were going to do it on Wednesday. So we have d minus O times O times 1 minus O. So you say, that's fine. That can get us, these weights here, even this WC. How are we going to get the deltas for the new weights here? Oh, I realize. Yeah, I got it. So the delta, by the way, this is the delta at C. How is neuron C contributing to the output? Well, it's directly contributing to the output, and it's got a sigmoid in it. It doesn't really, but we're pretending it does for now. D minus O times 1 minus O. What about an inner node? Node B, node A, what are we going to have to do? Well, the way they contribute to the output is that they contribute to node C. So we can do this problem recursively. So let's do it recursively. First of all, as you probably figured out, all of them are going to have an O times 1 minus O factor in from the chain rule because they're all sigmoids. Well, pretending that they're all sigmoids. So we actually have a dearth of good problems that are actually sigmoid on the web right now. There's only 2007. But here's O times 1 minus O. So what are we going to do for the rest of it? How does it contribute to our final result? Well, it contributes to our final result recursively. So we're talking about delta I. I is sort of an inner node. It's not a final node. It's somewhere along the way. So sum over J of W going from I to J times delta J. Now, sum over all J such that I leads to J. I need to have a direct path into J. So if I, in this instance, was A, everyone, the only possible J in this would be C. That's right. We would not sum over B as one of the J because I does not lead to B. Or A does not lead to B, A only leads to C. Also note that C does not lead to B here, that's going backwards. So you just, to figure out which J you're looking at, look directly forwards at the next one. So if there was another D here or something like that, A does not go to D, A goes to C. You only look at the next level's children, and you sum over all of those children, the weight between them multiplied by the child's delta. That makes sense, right? Because the way we affect, if the child's delta is the way the child affects the output, calling these children for a moment, if this one directly affects the output, then the way this one affects it is you use it affects it because it affects this, but it's also multiplied by this weight. So in fact, for instance, if the weight between A and C was 0, then A doesn't affect the output at all, right? because its weight is 0. And when we do this problem, we go this times 0, and then we try to add it in there. It doesn't affect anything. If its weight is very high, it's going to really dominate. It's going to really dominate it, see? And that is taken into account here, and then multiplied by the delta for the right node. So I pose the following question, and since I spent a lot of time with formulae and not that much time starting on the problem, I will not call on someone at random, but rather take a volunteer. And if no one volunteers, I'll eventually tell you, which is we've got some nice formulae for on the bottom 3. If we change the sigmoid function, what has to change?
The derivative of the sigmoid that
That's right. The only thing that changes in this crazy-ass problem right here, which, by the way, changes the sigmoid functions into adders, is that we take all of the O times 1 minus O in delta F and delta I equation, and we change it to the new derivative. We then do the exact same thing that we would have done. Correct. And on a similar note, if we change the performance function, how many of these equations at all have to change? All on the bottom 3. Yeah, that's right, just one, just delta F. Take the d minus O, make it the new derivative of the new performance function. And in fact, delta I doesn't change at all. Does everyone see that? Because it is very common for something to be replaced. I think 3 of the 4 quizzes that we have replaced in changed something in some way. All right, let's go. We're going to do 2008 quiz because it has a part at the end that screwed up everyone. And so let's make sure we get to that part. That's going to be the part that you probably care about the most at this point. So these are all adders instead of sigmoids. That means that they simply add up everything as normal for a normal neural net, and then there's no sigmoid threshold. They just give some kind of value. Question?
Yeah, so we're talking about like the A, B, and C nodes. Are the multiplier things, we don't count those as nodes?
They are not neural net nodes. That is one of the reasons why that other form that you can see over there is elegant. It only has the actual nodes on it. It's very compact. It's one of the forms we've used in previous tests. The question is, do those multipliers count as nodes? However, by not putting in the multipliers, we feel it sometimes confuses people of explicitness. The ones that are nodes will always have a label like A, or here you see there's a sigmoid and an L1. The multipliers are there for your convenience to remind you to multiply, and also those, if you look, those sigmas that are over there, you're there for your convenience to remind you to add. But in fact, the only thing that counts as a node in the neural net, and that's a very good question, is usually the sigmoids. Here it's the adders. We've essentially taken out the sigmoids. These adders are here's the way to tell. If it's got a threshold weight associated with it, then it's one of the actual nodes. A threshold weight. I guess the multipliers look like they have a weight, but this is just the weight that's being multiplied in. This is a weight that's being multiplied in with the input. But if it has a threshold weight, just like WA, WB, I promised I would tell you guys the difference between the 2 weights. So let's do that very quickly. The kind of weights that say W2B or W1A are a weight that comes between input 1 and A, or between A and C. They're meant to be multiplying the input by this weight, and then eventually that's added together. The threshold weights, they just have like WB, WA, WC. They are essentially to decide the threshold for a success or a failure, for a 1 or a 0, or anything in between, at any of the given nodes. So the idea is maybe you, at some node, want to have a really high cutoff. You have to have a very high value coming in, or else it's a 0. So you put a high threshold. The weight is multiplied by -1. And in fact, the threshold weight, one could consider, if you wanted to, that the threshold weight times -1 was also added in at that sum, instead of putting it at the same location as the node. If that works better for you when you're converting it, you can also think of it that way. because the threshold weight is essentially multiplied by -1 and added in at that same sum over there. So that is another way to do it. There's a lot of ways to visualize these neural nets. Just make sure you have a way that makes sense to you and that you can tell pretty much whatever we write, as long as it looks vaguely like that, how to get it in your mind into the representation that works for you. Because once you have the representation right for you, you're more than halfway to solving these guys. They aren't that bad. They just look nasty. They don't bite. Okay, so these are just adders. So if it's just an adder, then that means that if we take all the x inputs coming in, let's do x and y for the moment, so we can figure out the derivative. Then what comes out after we just add up the x, what comes out, y equals x, right? We're just adding it up. Adding up all the input, we're not doing anything to it. Y equals x is what this node does. Do people see that? So the derivative is just 1. So that's pretty easy because the first problem says, what is the new formula delta f? So I'll just tell you, you guys probably figured it out. It's O times 1 minus O. Because we replaced d minus O with 1. Okay? Makes sense so far? Please ask questions along the way because I'm not going to be asking you guys. I'll do it myself. Question?
Why do we replace d minus O with 1?
That's a good question. The reason is because I did the wrong thing. So, see? It's good that you guys are asking questions. It actually should be replacing O times 1 minus O with 1. The answer is delta F equals d minus O. So yes, perhaps I did it to trick you. No, I actually messed up. But yes, please ask questions along the way. Again, I don't have time to call on you guys at random to figure out if you guys are following along. So I'll do it myself. We're replacing the O times 1 minus O with 1 because of the fact that the sigmoid is gone. And we get just delta F equals d minus L. So, great. We now want to know what the equation is for delta I at the node A. So delta A. Well, let's take a look. The O times 1 minus O is gone. Now we just have the sum over J, which is, you guys already told me is only C, of WAC times delta C. And we know that delta C is d minus O. So the answer is delta A is just WAC times d minus O. That time I got it right. So I see the answer here, though it's written in a very different format from the old quiz. Any questions on that? Well, that's part A that we finished out of C. Let's go to part B. Part B is doing one step of backpropagation. There's almost always going to be one of these in here. So the first thing it asks is to figure out what the output O is for this neural net if all weights are initially 1 except that this guy right here is negative 0.5. All the other ones start off as 1. So let's do a step. Also, let's see what are the inputs. The inputs are also all 1. The desired output is also 1. And in fact, the rate constant alpha is also 1. This is the only thing that isn't 1, folks. So let's see what happens. 1 times 1 is 1. Then this is negative 1 times 1 is negative 1. That's 0. The exact same thing happens here because it's symmetrical. So these are both 0. 0 times 1 is 0. 0 times 1 is 0. Then this is negative 1 times negative 0.5 is positive 0.5. So 0 plus 0 plus positive 0.5, the output is positive 0.5. Does everyone see that? If not, you can convince yourself that it's positive 0.5. That would be a good exercise for you running through one forward run. The output is definitely positive 0.5 first time around. Okay? Now we have to do one step of backpropagation. To do that, let's calculate all the deltas so that we can calculate all the new weights, the new weight primes. So, delta C. That's easy. You guys can tell me what delta C is. We figured out what the new delta C is going to be. It's a simple addition or subtraction problem. Everyone, delta C is 0.5, 1/2. Yes. All right. And we know that delta A and delta B are just WAC times delta C and WBC times delta C. So they are also 1/2 because all the weights were 1. Easy street. Okay. We've got all the deltas are 1/2 and all but a few of the weights are 1. So let's figure out what the new weights are. So, okay. New WAC. Okay. So, yeah. So let's see. What's going to be the new WAC? So the new WAC is going to be old old WAC, which is 1, because all of them are 1 except for WC, plus the rate constant, which is 1, times the input coming in here. But remember, that was 0. So actually, it's just going to be the same as the old WAC. And since this is a symmetrical problem between B and A at the moment, this is going to be the same. All right. Some things are going to change, though. What about WC? That was the one that was actually not 1. Okay. So new WC, remember, the I for WC, the I that we use in this equation is always -1 because it's a threshold. So we have the old WC, which is -0.5, plus 1 times -1 times delta C, which is 1/2. So we have -0.5 plus -0.5 equals -1. W1A. Well, we've got W1A starts as 1. Then we also know that W1A is going to be equal to 1 plus 1 times the input, which is 1, times delta of A, which is 1/2. So 1.5. And since it's symmetrical between A and B, then W2B is also 1.5. And then finally, WA and WB, the offsets here, well, they start at 1 plus 1 times -1 times 0.5. So they're both, everyone? 1/2, that's right. That's right, because -1 is their I. -1 times 1/2 plus +1 is just 1/2. That's one full step. Maybe a mite easier than you might be used to seeing, but that's a full step. And it asks what's going to be the output after one step of backpropagation. Well, we can take a look. So we have 1 times the new W1A, which is 1.5. We've got 1.5. Then the new WA is just 0.5. Minus 0.5, that's a 1 coming into an adder. We've got another 1 coming in here because it's symmetrical. So a 1 and a 1. 1 times WAC is 1. 1 times WBC is 1. So we have 2 1s coming in here. They're added. That's 2. Then this has become -1, in fact, at this point. So -1 times -1, that's 3. And the output is 3. All right, cool. We've now finished part B, which is worth over half of everything. Oh, no, we've not. One more thing. These are adders. They're not sigmoids. What if we train this entire neural net to try to learn this data so that it can sort of draw a line on the graph or draw some lines or do some kind of learning to separate off the minuses from all the pluses? You've seen maybe, and if not, you're about to in a second because it asks you to do this in detail, that neural nets can usually draw one line on the graph for each of the sort of nodes in the net, because each of the nodes has some kind of threshold and you can do some logic between them like ands and ors. So what do you guys think this net is going to draw? If anyone could volunteer, I'm not going to ask anyone to give this answer. No? Okay, this is a little bit tricky because usually if you had this many nodes, you could easily draw like a box and box off the minuses from the pluses. However, it draws this, and it asks what is the error. The error is, oh yeah, it even tells you the error is 1/8 because why? These are all adders. You can't actually do anything logical because this entire net boils down to just one node because it just adds up every time and it never takes a threshold at any point. So you can't turn it into logical ones and zeros because it's not digital at all. It's analog. It's giving us some very high number. So it all boils down to one cutoff. And that's the best one, the one that I drew right here. Okay. Did that not make sense to you? That's okay. This problem is much harder. And putting them both on the same quiz was a bit brutal. But by the time you're done with this, you will understand what a neural net can do or not. I've put these in simplified form because of the fact that we don't care about their values or anything like that. But inside of these little circles is a sigmoid. The multipliers and the summers are implied, just so that I think in the simplified form, when we're not actually doing backpropagation, it's easier to view it and see how many nodes there are, for the same reason you asked your question about how many there are. So all of those big circles are a node, and in those nodes is a sigmoid now, not those crazy adders. We have the following problem. We have to try to match each of A, B, C, D, E, F to 1, 2, 3, 4, 5, 6, using each of them only once. That's important because of the fact that some of the more powerful networks in here can do a lot of these. So it's like, yes, the powerful networks could do some of the easier problems here, but we want to match each net to a problem it can do, and there is exactly one mapping that will map, that is 1-to-1 and maps uses all 6 of the nets to solve all 6 of these problems here. So some of you may be looking at it like, what? How am I going to solve these problems? I gave away a hint before, which is that each node in the neural net, each sigmoid node, can usually draw one line it can draw one line into the picture. The line can be diagonal if that node receives both of the inputs, which here are I1 and I2. You see there's an I1 and an I2 axis, like an X and a Y axis. The node has to be horizontal or vertical if the line has to be horizontal or vertical if the node only receives one of the inputs. And then, if you have a deeper level, these secondary level nodes can sort of do can do some kind of Boolean thing like and or of the first two, which can help you out. All right? And so let's try to figure it out. So right off the bat, and I'll hope that people will help and call this out because I know we don't have enough time that I can force you guys to all get it. Right off the bat, which one of these looks like is the easiest one? 6. That's great. 6 is definitely the easiest one. It's a single line. So this is just how I would have solved this problem, is find the easiest one. Now, which of these is the crappiest net? A. A is the crappiest net. In fact, there is no way in hell that A is going to be able to get any of these except for 6. So let's right off the bat say that 6 is A. All right, 6 is A. That's A. We don't have to worry about A. Okay, cool. Now let's look at some other ones that are very interesting. All the rest of these draw 2 lines. Well, these 3 draw 2 lines. These 3 draw 3 lines. They draw triangle. So, despite the fact that this C is a very powerful neural net indeed, with 3 whole levels here of sigmoids, it looks like there's only 2 nets in our little stable of nets that are equipped to handle number 1 and 2. And those are E and F. Because E and F have 3 nodes at the first level, they can draw 3 lines, and then they can do something logical about those lines, like for instance maybe if it's inside all of those lines. There's a way to do that. You just basically can give negative and positive weights as you so choose to make sure that it's under certain ones, above other ones, and then make the threshold such that it has to follow all 3 of your rules. So between E and F, Which one should be 2 and which one should be 1? Anyone see? Well, let's look at 2 and 1. Which one of these is easier to do between 2 and 1? 2. It's got a horizontal and a vertical. 1 has all 3 diagonal. And which one of these is a weaker net between E and F? F has one node that can only do a horizontal and one node that can only do a vertical line. So which one is F going to have to do? 2. And E does 1. Good job, guys. Good job, guys. You got this. So now let's look at the last 3. Number 3 is definitely the hardest. It's an XOR. Those of you who have played around with 002 kind of stuff or even just logic probably know that there is no way to make a sort of simple linear combination of in one level of logic to create an XOR. XOR is very difficult to create. There are some interesting problems involving trying to teach an XOR into a neural net. If the neural net is simple enough, it's just not going to be able to get the XOR because of the fact that you can tell it, okay, I want this one to be high and this one to be low. That's fine. You can say these both have to be high. That's fine. But it's hard to say, like, it's pretty much impossible to say this one or this one, but not the other because of need to be high in a single node because of the fact that if you just play with it, you'll see you need to set a threshold somewhere, and it's not going to be able to distinguish between. If the threshold is set such that the OR is going to work, the whole OR is going to work. It's going to accept when both of them are positive as well. So how are we going to do an XOR? We need more logic. We need to use some combinations of ANDs and ORs in a 2-level way. And to do that, we need the deepest neural net that we have. There's only one that's capable of that, and that is, it's C. So there are many different ways to do it. Let's think of a possibility. I1 and I2, draw these 2 lines. Or sorry, not I1, I2. These 2, let's call these 1, 2, 3, 4, 5. Of node 1 and node 2, draw these 2 lines. I'll just sort of draw it here for you guys. Then maybe node 3 gives value to, let me see. Node 3 can give value to perhaps, let's see, node 3 can give value to everything that is, there are a lot of possibilities here. Node 3 could give value to everything that is up here. Actually, node 3 could give value to everything except for this bottom part. And then node 4 could give value to, say, oh no, doesn't do it yet. But there's a few different ways to do it if you played around. The key idea is that node 3 and node 4 can give value to some combination of AND or not. And then node 5 can give value based on being above or below a certain threshold combination of 3 and 4. You can build an XOR out of the logic gates. I will ponder on that in the back burner for a moment as we continue onward, but clearly C has to do number 3. Okay, now we're left with 4 and 5. I think intrinsically 5 looks like it may be more complicated than 4 because of the fact that it needs to do both different directions instead of 2 of the same direction. However, however, just the idea of the one with the fewer lines being the simpler one may not get us through here, and there's a reason why. Look what we have left to use. We have to use D or B. What is the property of the 2 lines that D can draw? D being the simpler one. 1 horizontal and 1 vertical, that's right. So even though it may look simpler to just have 2 horizontal lines, it actually requires B. B is the only one that can draw 2 horizontal lines because D has to draw 1 horizontal and 1 vertical. So that leaves us with B on this, D on this, and excellent, we have a question. I would have thought it would be impossible we had no questions, or maybe I just explained this the best I ever have. Question?
I didn't get why B has to be 2 horizontal lines.
All right, so the question is, I don't understand why B has to be 2 horizontal lines. The answer is, it doesn't. B can be anything, but D can't be 2 horizontal lines. And so by process of elimination, it's B. Well, take a look at D, right? So D has 3 nodes. 1, 2, 3. Node 1 and node 2 can just draw a line anywhere they want involving the inputs they receive. What input does node 1 receive? Which inputs go to node 1? I1. Only I1. So it can only make a cutoff based on I1. So therefore, it can only draw, by making a cutoff above or below a certain point in I1, it can only draw a vertical line. Node 2 can only draw a horizontal line because it can only make a cutoff based on where it is in I2. Therefore, they can't both draw a horizontal. That's why this is the trickiest part, this last part, because B is more powerful. B does not only have to do 2 horizontal lines. It can do 2 diagonal lines. It can do anything it wants. It just happens that it's stuck doing this somewhat easier problem because of the fact it's the only one left that has the power to do it. So let's see. We're done, and we have aced this part of the quiz that like no one got. Well, not no one, but very few people got when we put it on in 2008. The only thing we have left to ask is, let me see. The only thing we have left to ask is, what are we going to do here for this? All right, let's see. For the XOR, let's see if I can do this XOR. So, okay. How about this one? Ready? I'm an idiot. This is the easiest way. Number 1 draws this line. Number 2 draws this line. Number 3 ands the line, the 2 lines. Number 3 says only if both of them are true will I accept. Number 4 knots the 2 lines. And number 5 ors between 3 and 4. Thank you. No, it's not that hard. I just completely blanked. Because there's another way that a lot of people like to do it that involves drawing in a lot of lines and then making the cutoff be 2, but I can't remember it at the moment. Are there any other questions? Because I think that if you have a question now, like 4 other people have it and just start raising their hands. So ask any questions about this drawing thing. Question? Why do we do this drawing thing? That is a very good question. The answer is so that you can see what kinds of nets you might need to use in these simple problems to answer these simple problems, so that if, Athena forbid, you have to use a neural net in a job somewhere to do some actual learning, and you see some sort of quality about the problem, you know not to make a net that's too simple, for instance. And you wouldn't want a net that's more complex than it has to be, so that you can sort of see what the nets do at each level and more visibly understand. I think a lot of the people who drew problems like this just want to make sure people know, oh yeah, it's not just these numbers that we're mindlessly back propagating from the other part of the problem to make them higher or lower. This is what we're doing at each level. This is the space that we're looking at. Each node is performing logic on the steps before, so that if you actually have to use a neural net later on down the road, well, then you'll be able to figure out what your net's going to need to look like. You'll be able to figure out what it's doing, at least as well as you can figure out what it's doing for a neural net, since it often will start getting out these really crazy numbers. You'll have all sorts of nodes in a real neural net that's being used nowadays. There will be tons of nodes, and you'll just see the numbers fluctuating wildly, and then suddenly it's going to start working or not. That's a good question. Any other questions? We still have a few minutes. Not many, but a few. Any other questions on any of this stuff? Question?
Sorry, this is a follow-up question on what you just asked.
Okay.
I'm just completely confused as to why a machine needs to learn by drawing pictures like that. Like,
okay.
You don't ask.
You're confused why the machine needs to learn by what? By the pictures on the right? Oh, okay. Machine does not have to learn by drawing pictures and calling them in. Let me give you some real applications. My friend at University of Maryland recently actually used neural nets because, yeah, he actually did. Because of the fact that he was doing a a game playing competition where the game was not known when you were designing your AI. It had to be able to, there was some very elegant general game solver thing that you had to be able to hook up into, and then they made up the rules, and you had a little bit of time, and then it started. So some of the AIs, what they did was, they trained once they found out what the rules were on their own with the rules. In his case, he had a neural net because it was so generic. You just have a web of random goop. He thought it could learn anything. And then he never did tell me how it went. It probably didn't go well, but maybe it did. It basically tried to learn some things about the rules. Some of the other people who were more principled game players actually tried to find out fundamental properties of the space of the rules by testing a few different things so that they could, more knowledge is less search, so that they could do less search when the actual game playing came on. And then when the actual game playing came on, pretty much everyone did some kind of game tree-based stuff. He's telling me that a lot of Monte Carlo-based game tree stuff that is this very non-deterministic is what they're doing nowadays rather than our more deterministic alpha beta, although he said it converges to alpha beta if you give it enough time. That's what he told me. But that's someone I know who is using neural nets. I've also, in a cognitive science class I took, saw neural nets that tried to attach like qualities to objects by having just this huge number of nodes in levels in between, and then eventually it was like a duck flies, and you're like, how is it doing this again? I'm not sure, but it is. So the basic idea is that one of the main reasons neural net were used so much back in the day is that people on many different sides of this problem, cognitive science, AI, whatever, were all seeing, wait a minute, there's networks of neurons and they can do stuff. And we're seeing it in different places. And when you see it in so many different places at once, it must be a genius idea that's going to revolutionize everything. And so then everyone started using them to try to connect all of these things together, which I think is a noble endeavor. But unfortunately, people just stopped using it. It didn't work as they had wanted. It turned out that figuring out how our neurons worked in our head was not the way to solve all AI hard problems at once. And they've fallen into disfavor, although are still used for some reasons like that. So we wouldn't use it just to draw these pictures. The reason why we have these pictures is because we give you simple nets that you can work out by hand on the quiz. Any net that was really used nowadays would make your head explode if we tried to make you do something with it on the quiz. It would just be horrible looking. So I think that's a good question. If there's no other questions, or even if there are, because we have to head out, if there's any other questions, you can see me as I'm walking out.